Hi everyone, I hope your winter break is going really well. I do apologize for not being able to have that very first day of school so that we can go over this lab. So I hope this video does do a good job at just kind of helping you out where I can. So anyway, let's take a look at the pre-lab for the kinetics of crystal violet fading. So pull it out, let's take a look. All right, question number one wants you to determine the optimum wavelength using Beer's law calibration curve for crystal violet that you see here in this image. So the thing that you have to remember, and we discussed this before, is that the machinery itself does not like to have an absorbance above 1.0. So when you're looking at this graph, what you need to consider is that you've got to be able to see an absorbance that is right at 1.0. So let me make sure I've got the right color here. So let me show you what they mean. So if you come right across the absorbance of 1, and when you hit the line, you want to drop down here. All right, if you look really closely, that wavelength right there is about 540 nanometers. Now, if you keep going on this graph, and you get to this second spot, where the absorbance does hit about 1, and you drop down, oops, sorry, not straight. That'll give you a second wavelength of about 610 nanometers. Now, both of these wavelengths are technically correct answers, and I wouldn't want to persuade you otherwise. But I don't know if you remember this, but lower wavelengths have a tendency to be a little bit more accurate on the machine itself. So instead of saying 610 nanometers, I'm going to go with the 540 because lower wavelengths seem to work a little bit better on the machine. Now the next thing you need to be aware of is that this absorbance was obtained from a concentration of 12.5 micrometers. So that's going to help us in that data table on question number 2. Question number 2 wants you, or sorry, question number 3. Question number 3 actually wants you to be able to use Beer's law to anticipate what the absorbance will be. And before we get there though, let's go ahead and look at question number 2 and just make sure you know how to fill in those particular problems real quick. So in question number 2, they tell you that your stock solution is going to be a concentration of 25 micromolar, and your end solution needs to be 10 milliliters. And they give you a bunch of different concentrations that they want you to dilute this stock solution to. So this is your stock, all right, and this is the final volume of your dilute solution. Dilute solution. And then they give you a bunch of different solutions that you need to dilute to, so why don't we go ahead and pick on this first one. They want you to get 2.5 micromolar. So we got to figure out how to make our final diluted solution have a concentration of 2.5 micromolar, and then here's your stock solution. You got to figure out how much you need to use. I think you guys might know how to do this. Does this look familiar? M1V1 is equal to M2V2. Yes. Okay, so the original concentration of your stock solution is going to be 25 micromolar. You don't know how much of this stock solution you need, but you know the end result should give you a 2.5 micromolar, and your final volume needs to be 10 milliliters, and you can just arbitrarily just put a 10 right there. All right, so go through some math, grab your calculator, check your work, and now that you know the formula, the general formula for all of those, these should be really easy. Just remember, the missing volume that you're solving for is going to be the volume of the concentrate. You also need to put how much water you need to add to that concentrate. Just remember, the final solution needs to be 10 milliliters, and you are solving for a much smaller amount. All right, and that smaller amount is the volume of your concentrated solution. All right, so let's move on to that last question, question number 3. So keep in mind we're trying to use Beer's law. And in Beer's law, we have a generalized formula of absorbance is equal to A, B, and C. So absorbance is a number that we expect to see a value of less than 1, or 1.0 or less. And let's see. A, the lowercase a, is something called the molar absorptivity coefficient. Good grief. B is the path length in centimeters, and C is concentration in moles per liter. All right, now one of the things that you need to be aware of is that A and B, if they are held constant between each trial, and we can calculate that constant if we are, aware of the situation that at the beginning of the lab, we looked at an absorbance of 1.0. I don't know if you remember that. And the concentration of that solution at 1.0, they said was, if you look back at the video, was 12.5 micromolar. Okay, so technically we want our absorbance to be less than 1.0. There's a good reason for that, and I'll explain that later in class. But if you go back to the graph, technically what we'd want to do is, instead of using an absorbance of 1.0, we would technically want to look at something like 0.98 or maybe 0.99. We never want the absorbance to actually hit 1.0. And the math behind that is, well, silly. So looking at that graph, though, I'm not going to be able to get much more accurate than a 1.0. So anyway, with this, what we'll do is we will call AB, this lowercase ab, we will call this x, because it's a constant. So let's solve for x with the very first piece that we have. We have an absorbance of 1.0, we have an x, and the concentration there was 12.5 micromolar. So let's solve for that x. So when you solve for x, you should get a value of 0.08. Now that we have this AB constant, we can use it on any of these other problems. So what I'm going to do is I'm going to use this in sample A right here, and let's take a look at what that will look like. So what we're going to say is absorbency is equal to ABC. We don't know what the absorbency is, but we know that the lowercase ab is, this part right here is 0.08, and we also know that the concentration is 2.5 micromolar. All right, so when you solve for absorbance, your absorbance should give you a value of 0.20. So we can fill in 0.20 for the expected absorbance for solution A. And now that you guys know how to do one, you should be able to do the rest of them by yourself. All right, you guys, good luck. I really hope this helped you out, and I can't wait to see you guys again on Wednesday. Take care. Make sure you come in early, okay? Wednesday is an early lab. See you guys later. Bye.